Welcome to this on-demand webcast, The Power of S Parameters for High-Speed Digital Design. It's a version of a live tutorial session at the 2012 IEEE Symposium on Electromagnetic Compatibility. My name is Colin Warwick and I am a product manager at Agilent Technologies. In high-speed digital design, we're trying to get a multi-gigabit serialized stream from one chip to another. Rather than cut and try using breadboarding, we want to gain insight and do what-if design space exploration using simulation. The brute force approach might be to solve Maxwell's equations for the whole system, but there are at least two reasons why this approach simply won't work. The first reason is obvious, especially for a whole system. Maxwell's equations are way too computationally expensive to solve. But the second reason is not so obvious. It's a business reason to do with intellectual property. Components in this end-to-end system come from up and down a supply chain, and each company in the supply chain has intellectual property to protect, and they won't share the exact geometry and materials of their design, and this information would be necessary to solve for Maxwell's equations. So S-parameter models help solve both of these problems by abstracting the behavior of a particular component away from its implementation, and it does this in a way that is both computationally efficient and it also hides the intellectual property of the component vendor. So here are some characteristics of a successful modeling technology that seeks to divide and conquer, to divide up this chain into models. The first thing is the models must be shareable up and down the supply chain. They must be portable, black box models that hide the owner's intellectual property and are portable in the sense that they can run in multiple EDA tools. They must be behavioral models to make them computationally simple. If you try to model every aspect of implementation, the computational times will become prohibitive. They must also capture interaction between the models that are collected into your end-to-end system. This is a very important point that is very deceptive in the sense you're thinking about a signal going from this transmitter left to right, kind of unidirectionally towards the receiver, but in fact nature doesn't care about your goal of being a unilateral system. This is actually a bilateral system. You get reflections off of all these components, and there are signals actually moving from left to right and from right to left, and you have to take these into account because they affect the end result here, because you can get a reflection here, bounces off this component, and it adds up here at the receiver, which is the signal we're interested in. So we must capture interactions, in particular bilateral interactions that include reflections in your system. S-parameters is one way of doing this. So here's the agenda for the rest of the webcast. I'm going to talk about what makes a good modeling methodology. We'll talk about a little bit about lumped element netlists. Spice netlists have been used quite a bit. But what we find is at high frequencies we have to take the distributed nature of the components into account, and so people are moving increasingly to network parameters. I'll start off with an introduction in Z parameters. These aren't used very much anymore, but it's a good introduction. They use voltage and current state variables to characterize the interaction between components. I'll be talking mainly about S parameters. They use a different set of state variables called the power waves, the A and B power waves. It turns out you need two state variables to model a bilateral system. And after talking about an introduction to S parameters, we'll show how you can extend the idea of two-port S parameters to multi-port networks, extend the idea to not only single-ended but differential S parameters or mixed mode S parameters. And then finally I'm going to talk in some detail about S parameters in the time domain. S parameters are fundamentally a frequency domain metric. But in high-speed digital, we're interested in the time domain. We want to see an eye diagram and rise times and jitter and so on. These are all time domain characteristics, so we have to bring this frequency domain S-parameter model into the time domain to make use of it in high-speed digital. And it turned out this is quite tricky, so I'll spend some time talking about this. Now, one of the things that people who studied logic find quite tricky about S-parameters is that they're bilateral. They're not like unilateral transfer functions that you get in logic blocks or in C code, where you pass an input into the block and you get an output. But then the output in a unilateral system doesn't affect the input. There's no kind of back propagation of the signal. And this can be approximately true in logic because you're using MOSFETs that have Pretty close approximation to a voltage control current source, which is unilateral, at least in principle. In PCB traces and packages, this is far from the case. You have a true bilateral system. In fact, PCB trace is actually reciprocal, which is the kind of limiting case of bilateral. And when you have this bilateral characteristic, you have to have two parameters per port and not one. You can characterize the input of a unilateral block with just a single parameter x, the input. In a bilateral system, you need two parameters per port. For example, here I've just got a simple one-port Z network. It's in some kind of unknown environment, maybe a test environment, maybe it's been in use as a terminator or something. To characterize this system in measurement, we can have to measure the current and the voltage across the port, and that would give us our kind of Ohm's law characterization. It would give us this Z11 parameter. In use, we know the Z11 parameter. We've already measured it, and then we have two unknowns. Both the current and voltage are unknown. The Z is now a known measured variable, and we need another equation to solve the system. So you end up with lots of simultaneous equations. You need obviously one equation per unknown. In the case of measurement, there's only one unknown here. This is the Z, and because the measurement, the V and the I are known. But in usage, we have two unknowns, so we need a second equation to solve this system. And this second equation to resolve the two unknowns will come from the environment. So when thinking about network parameters, it's worthwhile thinking about two steps: the measurement and then the usage phase. When I'm measuring a network parameter like this very simple one-port Z component, I have some kind of known current source, say a 1 amp current source, so I know that the current going in is 1. I can measure the voltage across the port, and then using Ohm's law determine the Z parameter. So in that case it's pretty simple. But when I go to use this component, things get a little more complicated, because now I know my Z, I've already measured it, but now I have two unknowns. I have the unknown current and the unknown voltage. I need another equation to solve for these two unknowns. So in this system, I've got some kind of driver. Let's say this is my chip driver. It's a voltage source with a known output impedance. This gives me the second equation here. I know that V1 is the voltage source minus the voltage drop across the output impedance of the transmitter, the driver. I have my Ohm's law from my one-port terminator. I've got now two equations, two unknowns. I can solve for the input voltage. I get a voltage gain here, V1 over Vs, equal to the simple voltage divider equation. So that's not too bad, but you have to bear in mind, always when you're doing these equations, how many unknowns do I have and how many equations do I need? So let's now go to two-port Z parameters. Here we have four unknowns, because the two currents and two voltages appear at both ports. We have some kind of environment. Maybe it's a measurement environment or a usage environment. I haven't specified on this slide. But in any case, if I'm measuring Z parameters, I now have four unknowns. If I'm using Z parameters of a known two-port Z parameter block, I also have four unknowns, in this case two currents and two voltages. So creeping up a little bit in complexity now, let's look at the two-port Z parameter in kind of measurement mode. Again, I put a known current source, and I can measure this voltage on my measurement setup. And I'm going to leave the other port in this measurement setup open. That will set my I2 current by definition to 0 for open. This is very convenient because now with two measurements of the voltage at port 1, the voltage at port 2, by leaving this open, I can set the current here to 0, and now it's very simple to determine my Z11 and Z21, because I've got a 1 amp current source on port 1 and a 0 amp current source, an open, on port 2. So it's trivial to calculate now, having measured V1 and V2 and these known currents, to calculate Z11 and Z21. But that's only two of the four parameters. I need a new setup to measure the other two of the four parameters. And as you might guess, I now leave this port 1 open, put the 1 amp current source on port 2. That sets my currents to the opposite arrangement as previously. It zeroes out Z11 and Z21 and lets me determine Z22 and Z12. Just by simply measuring these two voltages again, I can get at the Z parameters. So two measurements, setups. On each measurement setup I measure two voltages. I can get sufficient equations to measure my four unknowns, the Z parameters. You'll notice in measurement you get to choose. You have a lot of flexibility, and people will choose the most convenient set of parameters to get at the unknowns that they need to get at. When you're using Z parameters, you don't have that flexibility because the system is kind of determined for you. So just to check your understanding so far, as an exercise, I want you to be the test set. Eric Bogerson always says be the signal. In this case, we're going to be the test set. I want you to imagine that our Z parameters consist of a shunt resistor of value R, and go through these equations and make sure you can solve for the Z parameters of a shunt resistor R. And when you're doing that, it's worth thinking about, did you have to measure the currents? When we get into S parameters, we'll be thinking about the sources and the voltages we measure. And it's worth thinking about, are we having to measure these currents, or do we get them from choosing our sources carefully? So go ahead and pause the video and see if you can get the right answer. So welcome back. If you did the exercise and you got the Z parameters of shunt R of being R for the Z11 through Z22, congratulations, you're now a certified test set. And let's move on now to using these Z parameters that we've measured in an actual chip-to-chip link. So let's imagine we're using this particular component in our end-to-end link. We've got a very simplified transmitter and receiver. Let's say the vendor of a PCB or a package or a connector or something has measured the Z parameters of their component. They don't want to tell you the exact geometry and materials properties, but they will send you this network parameter model. Now you want to plug it into an end-to-end system. And so you need to solve a bunch of simultaneous equations. Now things are getting a little bit more complicated. Now we have four equations. The manufacturer of this channel component gave us these four Z parameters, so they're now knowns. But the test setup has now gone away. You look inside the box that you received from the vendor. There's no test setup comes with a component. Now the component's plugged into a completely new environment. So all the 1 amp current sources and 0 amp current sources have gone away. We're going to plug this component in our system, and so the I's and V's are going to be different. And obviously we only get two equations and four unknowns from the Z parameters themselves. We need two more equations to solve the system, and these are going to come from the source and the load. The source equation is the same we had before with the terminator. It's just the source voltage less the voltage drop across the output impedance. And the load equation is even simpler because there's no voltage driver. It's just Ohm's law across the load impedance. So now we have four equations, four unknowns we can solve for voltage gain. We can measure the voltage gain of this channel, V2 divided by Vs, and it's if you plug in the algebra, it comes out this fairly simple equation here. And you'll notice that the voltage gain depends not only on every one of the Z parameters, but also the load impedance, and also the source impedance, of course. So all of these 6 parameters come into the voltage gain. We'll remember that for when we get to S parameters. So again, just to test your understanding, pause the video and do this exercise. Instead of being the test setup, we're not going to be the signal, we're not going to be the test setup, we're going to be the EDA tool. Let's imagine that we've received a manufacturer's model of a channel against this series, this shunt R resistor, excuse me. And we're going to try and solve for the voltage gain as if we're using an EDA simulator that can handle Z parameters and solve for the voltage gain. So we can plug these four equations in and try it with a shunt R Z parameters, which was these four elements we calculated previously. And you might want to plug in some limits, solve for voltage gain when the output impedance is equal to the load impedance is equal to R, for example, or in the limit of R being much greater than ZL and ZS. Plug it into these equations and just explore a little bit what an EDA tool is doing when it's receiving a component like this into an end-to-end simulation and solving for something like voltage gain. So this is going pretty well so far. We have Z parameters, we understand them, we know how to measure them, how to use them, and they give us this kind of shareable IP protected models. You can send them off in portable industry standard model formats, Touchstone or CITI files. They're machine readable, human readable, they're just ASCII files. They contain only behavioral information. There's no implementation detail about the geometry of the connector or the material properties used. It's just the behavior in a circuit. So you don't need encryption, and you can, without any encryption, you can make a model that's portable across multiple EDA tools. So why don't we just use Z parameters? Well, there are a couple of problems. Let's explore why we don't use Z parameters very much. So I want you to be the test set again. This time I want you to do a series R and try and calculate the Z parameters for a series R. Just pause the video and try to do that. So welcome back again. I think you've discovered that one of the weaknesses of Z parameters is they're not defined for a series impedance. But you can use another variant on the Z parameter theme, which is Y parameters. This is admittance parameters, which is the inverse of the impedance parameters. And you measure these most conveniently by putting shorts across the most of the ports and a voltage source instead of a current source across the powered port. And this is a very convenient way to measure Y parameters. And you do the same trick as Z parameters. You have two measurement setups. You measure two parameters on each of the measurement setups. In this case, we'll measure current at port 1 and port 2. Redo the setup, measure current I primes. And we have four equations, four unknowns. We can measure the Y parameters. And they will work for series resistance. If you want to try it, you should get this answer for a series resistance. The Y parameters should be 1 over R in all four cases. Now, as you've seen, there are some limitations with Z and Y parameters. There's a few more limitations with them. You can most conveniently measure Z and Y parameters with opens and shorts, but it turns out that opens and shorts are hard to create at a high frequency. An open has a parasitic capacitor. There's a fundamental quantity of space, the permittivity of free space, which is about 9 femtofarads per millimeter. So if you have like a little stub pair of parallel wires millimeter long, you'll have this parasitic capacitance, and this brings the if you have say 20 femtofarads at 10 gigahertz, that brings your impedance to 800 J ohms, which is down from infinity at DC. A short has a parasitic inductance. There's a permeability of free space, which is about a nanohenry per millimeter. So if you have even a small inductance, 1 nanohenry at 10 gigahertz is 63 J ohms, and that's up from 0 at DC for a millimeter long wire or a few millimeters of wire. So there's a problem creating opens and shorts, and this makes it hard to measure Z and Y parameters accurately, because to measure them accurately you need an open and a short, otherwise you end up trying to solve equations that are slightly non-orthogonal. It's possible, but there's a measurement error introduced. The other issue with real-world ports is they have an antenna effect, or a series antenna. A dipole with its wavelength much bigger than the length of the antenna has an antenna series resistance, and for 30 millimeters that's about an ohm, where Z0 is the vacuum impedance. 377 ohms is a fundamental quantity of free space. So we're looking for a way that avoids opens and shorts if possible, because they are hard to create at high frequency and they introduce a measurement inaccuracy. Opens and shorts can cause other problems too, particularly in active devices like power amplifiers. They can oscillate or even burn up if you put an open and a short on them to measure them. So people tend to want to avoid that. They want to use an impedance which is closer to the real world use case impedance. So this is another problem with opens and shorts. It doesn't particularly affect high-speed digital cases because you're generally measuring passive devices, but in RF power amplifiers this can be problematic. Now it's certainly true you can measure Z parameters without using opens, and you can measure Y parameters without shorts also. Instead of using a current source, you use a kind of loaded source with some kind of reference impedance. And the problem with this is you end up with a set of equations. You still have 4 equations, 4 unknowns, but you haven't zeroed out any of these things. And to solve these equations, you end up subtracting some very large numbers, subtracting voltages, subtracting currents. When you have a measurement set up, there's an error in the voltage and an error in the current, and by subtracting 2 measurements that both have errors in them, you end up with a bigger error. The error can compound. So this is not an ideal way of measuring Z parameters, because you end up having to subtract 2 large numbers, and that can compound the measurement error. Can be done, but it's not the optimum way of doing it. Similarly, you can measure Y parameters without shorts. Again, you put some kind of reference impedance, and again you end up subtracting noisy measurements and building up the measurement error. So this is not a recommended procedure. So this is all building up to S parameters. S parameters were proposed by a number of scientists. Probably the most famous one is Robert Dicke, who developed these in the MIT radiation lab during World War II, working on radar. After World War II, he was able to publish the work. By that time he'd moved to Princeton, published the work in 1947, and this is the first real paper that's recognizable as S parameters as we know them today. And what he did was he avoided this measurement problem with the opens and shorts by, instead of defining his parameters in terms of I and V, he chose a linear combination of I and V called the power waves, which are A and B. And these are something you can measure very accurately with a reference impedance in place. So you can avoid the opens and shorts, but you can null out the incident and reflected wave and get a very accurate measurement without subtracting 2 large noisy numbers. So this was the breakthrough of S parameters. Now physically, these A and B parameters, these state variables for each port, are actually power waves on a measurement setup with a cable of a characteristic impedance equal to the reference impedance. But I'm going to introduce them just algebraically. I'm going to say that I'm going to define A and B just completely algebraically in terms of the voltage and current at each port, and I'm going to make this reference impedance an arbitrary real positive number in ohms, but it doesn't correspond to any physical characteristic of the test setup. It's just some arbitrary number we chose. I'm going to define A and B in terms of these algebraic equations based on the current and voltage of the port. And it turns out with these definitions, the voltage is equal to the characteristic impedance square root, the sum of the power waves, and the current is the difference of the power waves divided by this normalization factor. And under these circumstances, our S parameters are then defined as the incident power waves multiplied by the S parameters give me the reflected power waves defined by this algebraic equation. So just like the Z parameters, let's think about these 2-port S parameters. I haven't defined the environment yet. Haven't said yet whether this is a measurement environment or a usage environment. But let's just think about how many equations we have here and how many unknowns. I'm going to define the power waves in this algebraic method in terms of the V and I, for reasons you'll see in a second. In a measurement situation, the unknowns are the S parameters, and my job is going to be figuring out a way of setting these algebraic equations in parentheses to either 1 or 0 to minimize my measurement error. In a usage situation, I'll know the S parameters because I've already measured them, and I'll be solving for the V and I using simultaneous equations and algebra and so on. So just as with the Z parameters, let's think about this in two steps. Let's think about measuring the S parameters where I know the voltages and currents because I have a test setup, and I want to determine the S parameters. And it's most convenient if I can figure out a way in the first test setup of setting this prefactor to 0 and 1 and then reversing it in the second setup, because then I can not have to do any subtraction and introduce measurement error. So if we think about it, how do I set this value to be equal to 1? Well, it turns out if I have a 1 volt voltage source and a real resistor now of equal to the reference impedance, that will set up this value to be equal to 1. Similarly, if I have no voltage source and just a reference impedance connected to the port, that will force this prefactor to be equal to 0. So now I can trivially just measure the these two voltage, this 1 voltage and current, and I can get at my S11 and S21 by making two measurements at the two ports. And I don't even need to measure the current, because if I've measured the voltage here, I know the current because my reference impedance is known. So this is pretty easy to do. The second test setup, I would just reverse the connections at the ports. I have a 1 volt voltage source with a characteristic impedance, an output impedance equal to the characteristic impedance. That forces my prefactors here to be 1. And I put a reference impedance on the port number 1, and that forces my prefactors here to be 0. So I can trivially determine now my S12 and S22 in this situation. So with two setups, two measurements in each setup, I can determine the 4 equations, the 4 unknowns. I know all my S parameters. So now the exercise, just pause the video, and now we're going to be a vector network analyzer, a VNA, and I'll give you the problem again of a series R. I want you to try and figure out the S parameters of a series R, and this is the test setup. These are the equations we have to solve. And think about, do you have to measure the I's? Can you just measure the V's, and can you determine the I without measuring it? Turns out you can. With a little thought, you can figure out a way of doing that based on the fact that you know that this output impedance of the 1 volt voltage source in my test setup has been chosen to be equal to the characteristic impedance of the S parameters that we're determining to measure. So welcome back. If your calculations came out to be equal to this, you're now a fully qualified vector network analyzer. This is the S parameters for a series impedance of resistance R, given that the S parameters have a characteristic, or sorry, a reference impedance, excuse me, ZR. Now if you remember, with the Z parameter we had an issue that they could do series not shunt and shunt not series. That's not the case with the S parameters. They can handle shunt and series perfectly well, and if you want extra credit, you can redraw the diagram in slide 26 and figure out what the S parameters of a shunt resistance are. Turns out to be these equations. Notice that with S parameters, the equations always involve this reference impedance. You have to specify a reference impedance with S parameters. It's part of the specification. You can't just specify the matrix elements. You also have to specify the reference impedance that the S parameters are referred to. Okay, the component vendors measured the S parameters on their VNA. They've mailed you the component with the S parameter file, and you're going to use this in your end-to-end system as before, the transmitter and receiver. And the first thing you notice, of course, is that the test setup has gone away. The component vendor didn't mail you a VNA, and there are no ZR resistors anymore. You're going to plug this into your system with some arbitrary source and load impedance. So don't get confused about this ZR thing. They're only physically present in the test setup. Otherwise, when you're using them, the ZR, the reference impedance, is an algebraic concept, and there are no physical ZRs anywhere in this system. There's no transmission lines with a characteristic impedance of ZR. There's no sources or load or anything like that. When you're using S parameters, the ZR is a purely algebraic concept. So when we use this in our actual end-to-end transmitter, again we have the S parameters are now known. We have two equations from the S parameters themselves that represent the algebraic relationship of the voltage and current at the ports. But we have four unknowns. We have I1, V1, V2 and I2. So we need two more equations, just as we did in the Z parameter case. Again, these two equations come from the source and the load. The load is just the Ohm's law. Obviously the sign is defined to be into the port, so we get a negative here. And the source equation is the fact that we have a voltage here, which is the source voltage minus the voltage drop across the source impedance. So four equations, four unknowns. We can solve for things like voltage gain, which is V2 divided by Vs. The algebra gets a little bit tricky because you've got quite a few terms here. I published the algebra on my blog as Appendix A. It's a PDF, goes through all the algebra. And it turns out the equations is kind of similar in form to what we saw for the Z parameters. It's a little bit more involved. It involves all four S parameters. It involves the source and load impedance, and also this algebraic quantity, the reference impedance ZR. So it's a little bit more involved, but we can basically use S parameters in an EDA tool for answering questions like what's the voltage gain of the end-to-end system. Again, extra credit if you want to plug through the algebra and just plug it into this equation. If you had, say, a series resistor and the manufacturer gave you the S parameters for this two-port network with inside the black box is just a series resistance, if you take that values that we had before for a series resistance, you'll remember that from slide 27, plug the numbers into this rather large equation that you can derive with some effort algebraically. I did that in that PDF appendix. Turns out that we get it reduces to this nice voltage divider equation, which is what you'd expect because the load impedance is basically a voltage divider with regard to the sum of the source voltage, the channel resistance and the load impedance. So that works out pretty nicely, as you'd expect. Now, one of the reasons why we use S parameters is the A and B power waves are very measurement friendly. You can do some nice things with them, for example, by using a Wheatstone bridge and measuring the voltage across the Wheatstone bridge detector. We can measure the reflected wave directly. It subtracts off the incident power wave for us. The other nice thing we can do is to move the measurement plane. When you're measuring S parameters, you want the very sensitive voltmeter to be inside some kind of casing. But the measurement plane of the network parameters may be somewhere else on the lab bench. It turns out by putting a coax cable of characteristic impedance equal to the reference impedance, the only difference you make is you make a phase change between the voltages and currents at the measurement plane and the voltages and currents at the voltage detector plane. And it's very easy to calibrate these cables out. So that's a very nice feature of power waves, is you can move the measurement plane with a cable of characteristic impedance equal to the reference impedance, and with very little work you can calibrate out that cable. Same thing on the load side. You can move the load, which you want to measure the voltage across, of course, and you want to have the voltmeter in some kind of instrument case, you can move that measurement plane from the device under test to the voltmeter using a coax cable of characteristic impedance VR, and again calibrate the cable out pretty simply. On this diagram I didn't show the return path, but there's obviously the return path. All these grounds are hooked up. So that's some reasons why we use S parameters. They're extremely measurement friendly. The measurement friendliness comes in particularly in difficult cases where you have a case of heavy attenuation. Let's say we have a crosstalk channel and it's weakly coupled into the victim channel. The signal that will measure from this port to this port is going to be extremely small. It may be 60 dBs down. So you really want a methodology that, like those Wheatstone bridges, that measure the power waves without heavy algebra subtracting large numbers with noise on them. With VNA, the voltage is directly proportional to the power wave. So even if you have a very weak reflected wave, you can measure it pretty well. So this is another reason why S parameters are measurement friendly. They work even in the case where you have a heavy attenuation like a crosstalk situation. Particularly at high frequencies, the Wheatstone bridge method of separating the A and B wave kind of breaks down at higher frequencies. But there's another trick you can use called a directional coupler. This is a remarkable device. It's just some strip lines have a certain geometry, and they have the weird property that they cancel the incident wave out, and you can put a detector at this port here, and because of the way the waves add up and constructive and destructive interference, even though this is a completely passive device, there's no magical materials in here, it turns out you can put a detector at this port here and purely measure the reflected wave. The incident wave is simply cancelled out from this particular geometry. So this is extremely convenient for very high frequencies where the Wheatstone bridge lumped element method doesn't work very well. You can do this with a directional coupler and measure the B wave directly without any subtraction of voltage and currents, and even a very weak B wave from a crosstalk channel can be detected rather easily. Now, so far all the I's and V's I've been talking about, I haven't really specified whether these are DC or AC quantities, but of course to measure S parameters they do need to be complex numbers. And so how you measure a complex number is you have a measurement plane which is coming from your Wheatstone bridge or directional coupler, and you actually have a radio receiver, an RF mixer. You have a local oscillator which is the same frequency as the voltage source you generated. It was a let's say a unit amplitude zero phase voltage source. You mix it with some kind of local oscillator. Put it through a bandpass filter. This is what gives the VNA its great sensitivity, because you can have a narrow band detector, so you don't take in a lot of thermal noise. You put it through a second LO, which is the sum of the two LOs is equal to the source frequency, and this has two components. It's a quadrature mixer which have 90-degree phase offset. Again, you put it through a low pass filter, and you get the in-phase and quadrature voltages. So you can determine now the amplitude and phase from these I and Q quantities using pretty simple algebra. And of course the trick is that you have to use these quadrature mixers, and you can actually do these electronics either in analog. These days this is actually usually done digitally. You actually digitize the output of the mixer or output of the bandpass filter, and can calculate all this in the digital domain. But wherever way you do it, you're getting both an amplitude and phase from these I and Q branches. And a VNA will contain 3 or 4 of these vector voltmeters, depending on how you calibrate the system, and they'll be used to measure the A and B waves for the various ports. So a big advantage of measuring with power waves rather than I's and V's is, especially comes in at high frequency. At low voltage it's trivial to measure, at low frequency, it's trivial to measure I and V using just voltmeters and so on. At high frequencies, this kind of approximation breaks down. We have Maxwell Ampere's law is the magnetic field is not only generated by a current. Now you can actually generate a magnetic field from a changing electric field. So in the case of a waveguide, there's no center conductor. There's actually no free current anymore. The magnetic field is generated entirely by a changing electric field. And conversely, with Faraday's law, a changing magnetic field can generate an electric field. You don't need electrostatic charges anymore to generate the electric field, and the voltage become actually path dependent. You have to specify a path and integrate the electric field along that specified path to determine a voltage. So the voltage is path independent only in the electrostatic case where there's no changing magnetic field. In DC, obviously, this is true. A high frequency is far from true, and it's almost like this kind of Penrose staircase thing where the the field is no longer conservative. You can go round and round the loop and pick up energy if there's a changing magnetic field. It's cut in the loop. In this case, the magnetic field's coming out of the paper, out of the screen, and we have some kind of changing magnetic field. It could be the linear or sinusoidal. But the point is now that there's no electrostatic potential anymore. Voltage depends on the path. The nice thing about S parameters, of course, is because we're measuring these power waves, we avoid the need to measure specific voltage and current. We measure the power at the measurement plane, and that gives us a well-defined measurement. So we've talked about two-port S parameters. How can we generalize this to multi-port? And it's pretty simple to do. Rather than having two measurement setups, we now need one measurement setup per port, and we need to measure the A and B power waves at each port for every measurement setup. So we get a lot more matrix elements for a n-port S parameters. We end up with an n by n matrix for each frequency. But this measurement setup will give us the equations we need to determine all of those parameters. In this case, we have an 8-port system, so we have 64 S parameters. So we'll have 8 measurement setups. We'll power up each port in turn and measure the A and B power waves at each of the 8 ports for each of the 8 setups. So that will give us 8 by 8, 64 measurements, 64 unknowns. We can measure all the S parameters. So it gets a little bit tedious and involved, but you can generalize this to a multi-port measurement, at least in principle, very easily. And this sort of thing is very useful in high-speed digital, where you have maybe a victim channel going from ports 1 to 2, and 3 aggressor channels here going from ports 3 and 4, 5 and 6, 7, 8. So this is very typical. This particular one is single-ended. If you were a differential, then 1 to 2 and 3 to 4 would be your differential victim channel, and 5, 6, 7, 8 would be the differential aggressor channel. Speaking of single-ended and differential, you can actually specify differential or mixed mode S parameters. And in this case, you have, let's say you have a single-ended 4-port measurement with conventional S parameters, a 4x4 matrix. You can recast the same information as differential. Then you have kind of 2 ports. You pair up the ports into pairs. So 4 ports you pair up into 2 differential ports. And then you have the second parameter would then become a response, either differential or common mode response, whether the ports are going out of sync or in sync. And that again will give you these 16 parameters. You don't simplify things, you actually have the same number of parameters. You can just recast them as these 16 parameters. It's a fairly simple algebraic relationship between the single-ended and the differential S parameters. The nomenclature is obviously S for S parameters, either a D or a C for differential or common, so don't get confused between DC meaning direct current. This is differential common mode, mixed mode parameter, and then the port numbering as before, port 1 and 2. Now when you get into differential pairs, there's some nomenclature you have to be aware of between things called modes and signals, and I refer you to Eric's book, Signal and Power Integrity Simplified. He covers this in great detail, but very briefly, odd and even modes are intrinsic properties of the geometry of a differential pair. They're not determined at all by the measurement environment or the usage environment. They're intrinsic properties of the pair itself. Differential and common signals are imposed from the measurement environment or the usage environment. So this is where we talk about differential common signals, odd and even modes. Differential signal excites the odd mode only if the pair is symmetric. So if you have an asymmetric pair, which is the general case, a differential signal will not exactly be the same. It won't exactly excite the odd mode. It'll excite some linear combination of odd and even mode in the case of an asymmetric pair. But in the symmetric pair case, which is often the case in PCBs, or at least they're close to symmetric, a differential signal will indeed excite the odd mode, and this is probably the reason for the confusion in the symmetric case, which is not the general case. But in this special case of symmetry, the differential signal does excite the odd mode, but this is not a general rule. So again, see Eric's book if you want more detail about this, but bear in mind that there's this nomenclature you have to deal with when you're dealing not just with S parameters, with differential S parameters, but differential and common mode signals in general. Okay, now I want to change gears and think about S parameters in the time domain. In particular, band-limited S parameters are problematic in the time domain. And the reason why I want to get in the time domain is because we probably want to model a SerDes link with a transmitter, a through channel, and a receiver. We want to look at the eye diagram, which is fundamentally a time domain measurement. Maybe want to look at some aggressor channels that are coupled to my through channel. Look at crosstalk. In any case, we want to take this S parameter model and use it in a time domain simulation and see the eye diagram. This can be very tricky. So this is a very severe case. I'm going to look at the severe case, which is a band-limited inverse Fourier transform of a lossless transmission line. So a lossless transmission line wants to have its frequency response specified right up to infinity. There's no losses, and I'm going to band limit it and do the inverse transform. Now we all know about the Nyquist limit. In Fourier transforms, we get a finite kind of width of an inverse Fourier transform when we have a finite Fourier transform. But when I actually do this case, I do the inverse FFT on a lossless transmission line, I get these very, very severe problems. I get all of this, besides the Nyquist limit here, this is central core here, I get all this ringing, and the ringing extends not only into the positive time, where the impulse response is positive, it actually goes into negative time. So the according to this, the impulse response actually occurs before the impulse occurs. We get a non-causal behavior instead of a 10 nanoseconds delay, wherever this line was. The impulse response actually starts in negative time. So we have very severe problems. What's going on here? So let's get back to fundamentals and think about what the Fourier integral is telling us. What we're trying to do is to build a frequency response out of sinusoids. We're taking an impulse response, h of t, and multiplying it by some sine waves and cos waves, integrating them all over time, and we come up with a set of phases and amplitudes that we sum to build up our original impulse response. Now, with the impulse response, which by definition is 0 for negative time and some positive number for positive time, we have a severe problem when we're trying to make an impulse response out of sine waves. And the fundamental problem is this: all sinusoids start at minus infinity. How can you possibly construct an impulse response which wants to be 0 all the way up to time t equals 0 and then positive in the positive plane when you're trying to build it out of sinusoids that start at minus infinity? How could you possibly add up all these sine waves and cos waves and get it to exactly cancel out everywhere from minus infinity to 0, and yet still have a positive response beyond that. You think it might be impossible to build an impulse response that is causal out of sine waves, because the material you have to work with, every single one of them has a finite value at minus infinity. How can you possibly build an impulse response out of sine waves and cos waves? Well, it turns out not only is it possible, but it's mathematically rather easy to do it, and it's a very, very surprising result. You can get cancellation in the negative time range, but non-cancellation in the positive time range. So this is what we want to end up with. We want to end up with an impulse response. We want to build it out of adding up a set of sinusoids. We want the sinusoids to cancel out at negative time, but have some kind of positive value at positive time. What set of sinusoids could we add up to make this kind of causal impulse response? And we know that every single sine wave has a finite value at minus negative time. Well, it turns out that this seemingly impossible task is not only possible, but there's a specific recipe for doing it. It's called the Kramers-Kronig relationship, and it gives you a recipe to build a causal impulse response out of sine waves and cos waves. And this is the kind of recipe how we step through it. The first thing we have to realize is that all functions, no matter what they are, can be trivially decomposed into the sum of an even and an odd function. The definition of an even and odd function, reminder, is that an even function is equal to itself if you just flip the on the time axis. An odd function, you do the same kind of time flip, but now it's equal to the negative amplitude of itself. That's the even and odd functions. I'll show you how to do that. Decompose the any function. It's trivial to decompose into an even and odd part. The second thing we have to realize is that if and only if the even part of a function is equal to the signum function times the odd part, then the function is causal. Now, signum is simply a function that is -1 for negative time and +1 for positive time. It's just a step function. The mathematically it's called the signum function. And I'll show you how that works out. If the even and odd parts are related in this way, then the function is causal. In particular, the amplitude is identically 0 for all negative time. The next thing we're going to work on is the fact that the odd part of the function can be made from sine waves, and the signum function can also be made by adding sine waves, and the even part can then be built up by multiplying the two, just by this methodology. So we'll take this recipe, 5 steps, and we'll break it down step by step and see how we can use the Kramers-Kronig recipe. Okay, step 1. Decompose the function into an odd part and an even part. Now it's trivial, if you just examine this algebra, it's trivial to see that the sum of these two parts equal the original function. Doesn't matter what the function is. And also that this, by definition, is even, and this, by definition, is odd. You can convince yourself of that pretty easily. So that's the first step. It's very easy to decompose any function, whether it's causal or not, into two parts, even and odd, defined this way. So step 2, we can build the odd part of any function out of sine waves. Sine waves are odd, and by adding the sine waves up, you can build up the odd part of the function. You can kind of visually imagine it in this way. Similarly, this signum function, which is just a step function, is also an odd function, and by adding the enough sine waves up, you can get a good approximation for the signum function, which is also odd. So the signum function can be built up with sine waves. Now, if I multiply my signum function by my odd function, I get this even function. I've basically just flipped the left-hand half of this chart, and I get an even function. You can see it's symmetrical around time t equals 0. So odd function times an odd function gives an even function, and this gives me my even function. Now here's a special case for a causal function. If I add that product of the signum function times the odd plus the odd function, the left-hand halves exactly cancel. If you remember, the left-hand half of my even function was just a flip over of the left-hand half of my odd function. So when I add them together, they cancel. So I have a causal impulse response. I decompose it into an even part and odd part. The even part was the signum function multiplied by the odd part, and then we've added in the odd part again. So now I've got my causal response, and I've decomposed it in this way. So now what? Well, the even function, which was cosine-like in the time domain, yields the real part of the frequency domain response. If you remember the definition of the Fourier transform, it's the cosines that give the real part of the frequency response. The odd part, which is sine-like in the time domain, yields the imaginary part of the frequency domain response. Again, the definition of Fourier transform is that the imaginary part comes from these sine waves. So even times odd integrates to 0, and we're left with these functions. The even part of my transfer function in the frequency domain corresponds to the cosine part, which is real, and the odd part multiplied by the sine waves gives me the imaginary part. Okay, yes, but really, so what? So the imaginary part in frequency is coming from the odd part in time. So this is the Fourier transform of the odd part. I've done it uppercase H. The real part in frequency has a specific relationship to the odd part given by the Hilbert transform. Remember, my even part was signum times H0 in the time domain. In the frequency domain, it's the Fourier transform of signum, which is uppercase signum in omega, convolved with the odd part of the Fourier transform, and this is called the this convolution is called the Hilbert transform. It's just 2 over j integrated over some dummy variable omega prime. So the sinc function we saw isn't just Nyquist, it's because band-limited data doesn't satisfy this relationship. So we have a problem. Band-limited data doesn't satisfy the Kramers-Kronig relationship, and it can never lead to a causal impulse response in the time domain. It's just impossible. So what can we do about it? Well, one thing you can do is kind of window the data and kind of put some kind of window in the frequency domain. You get less skirts, of the sinc kind of pulses are diminished slightly. But the central pulse, this Nyquist limited pulse, is actually broader. It's actually because you've reduced the bandwidth. Now the Nyquist limit, the central pulse gets broader, and it gets broader in both directions. It actually goes into negative time and positive time. So the pulse is not delay causal. Actually, energy is occurring before it could possibly reach the receiver at the speed of light if you do windowing. So windowing actually makes things worse. It looks a little bit better, gets rid of all this kind of ringing, but half the energy is still non-causal. It's smearing the pulse out, and it smears it out in both directions, both positive and negative time, and you still have this non-causal effect, and that will give you the wrong eye diagram shape. So this windowing doesn't work. It actually makes things worse. But fortunately, there is a good solution. It's published in this United States patent called the Rao Method, and its title of the patent is Optimization of Spectrum Extrapolation of a Causal Impulse Response using the Hilbert transform. We're actually going to use this Kramers-Kronig's property to create a causal impulse response from the frequency domain data. And here's a comparison of the results of applying the method. If I take a lossless delay line, 1 nanosecond grid points, and do this kind of brick wall IFFT, I get this Nyquist limited pulse, but with all this ringing because of the violation of Kramers-Kronig and the violation of causality. With the Rao method, I get a Nyquist limited pulse with no ringing and no pre-effect, no delay causal response. The voltage at 11 nanoseconds is exactly 0. And here's a second comparison now. Instead of the brick wall IFFT, this is the windowed IFFT. I mentioned that this actually makes things worse. You can see that the pulse is smeared into negative time and has a finite value even at 7 nanoseconds before the speed of light pulse could even arrive. The windowed FFT is responding. Again, same comparison with the Rao method. We get no pre-excursion of the pulse. So the way the method works is we extrapolate the band-limited parameters in the frequency domain, and we extrapolate the amplitude according to the decay of the amplitude of the given S parameters, and we construct a phase relationship from that extrapolated amplitude which satisfies the Kramers-Kronig relationship using that mathematical relationship between the odd and even parts of the functions. So the extrapolated frequency response is now that of a causal system. We apply the IFFT to the much wider bandwidth of extrapolated frequency response, and we end up with this causal impulse response in the time domain. So that's how the methodology works. So I really recommend this method if you're trying to get band-limited data into the time domain. This is really the way to go. And if you don't do this, you'll end up with the eye diagram, which is not correct. So here's some conclusions. The benefits of using S parameters is they're extremely measurement friendly, especially in the multi-gigabit regime. They take into account all the RF microwave effects that happen at gigahertz frequencies, where the wavelength is small compared to the device under test, and it takes into account reflections and so on. They're behavioral models that provide IP protection without the need for encryption. And because you don't need to encrypt them, they're portable. You can use divide and conquer methodology up and down the supply chain to receive these portable models from your vendors, from connector vendors, PCB vendors, and so on. The biggest caveat using S parameters, I found that people, because there's a reference, an algebraic reference impedance involved with S parameters, they somehow want to include that Z reference as a physical component in the system. That's a big mistake. The physical value of ZRef is used in the measurement setup, such as the characteristic impedance of the cables or the source and load impedance of the voltage measurements on the VNA. But you do not incorporate that physical component into your usage model when you're using S parameters in the system. So bear in mind, you need to separate the measurement case from the usage case. The usage case doesn't include any physical Z impedance. It's just an algebraic quantity. So remember that, and you'll be able to be successful using S parameters in your high-speed digital system. Thank you very much for your attention.